Welcome to our next session, which is a distinguished address on the theme India's Scientific Imprint on the Globe. From the pioneering contributions of ancient India in mathematics, astronomy, and medicine to today's advances in space technology, digital innovation, and biotechnology, India's journey of progress is one of continuity and transformation. In a world where science and technology increasingly determine power, development, and equity, India's role as both a contributor and a collaborator carries renewed significance. Today, we reflect on that legacy, its global resonance, and its future direction. It is my privilege to welcome Professor Amitabh Mattoo, Dean of School of International Studies, Jawaharlal Nehru University. Professor Mattoo will be chairing this session. Our distinguished speaker for this session is Professor Manjul Bhargava, a professor of mathematics at Princeton University. One of the foremost mathematicians of our time, he is the recipient of numerous recognitions for his contributions, including the Fields Medal in 2014, the highest honor in the field of mathematics known as the Nobel Prize of Mathematics. He was awarded the Padma Bhushan by the Government of India in 2015. Sir also holds a strong interest in arts, particularly music, poetry, linguistics, magic, history of science, and education. He is a member of Prime Minister's Science, Technology, and Innovation Advisory Council and serves as the chair for the Education Advisory Council to the Ministry of Education. I now invite Professor Mattoo to welcome our guest with flowers. Welcome, Professor Bhargava. We are eager to hear from you. I request Professor Dean Mattoo to take over the proceedings.
Namaskar, good morning. It's not every day that you get the pleasure of chairing a session by one of the most extraordinary minds that India has produced. We have really, truly privileged and honored to have with us Professor Manjul Bhargava, as who you heard is Fields Medal laureate and Professor of Mathematics at Princeton University and Education Advisor to the Government of India. I also want to acknowledge Dr. Priyadarshi Bhargava, who is an alumnus, and I suspect that one of the reasons why I was able to persuade Professor Manjul Bhargava to spare the time was because his spouse may have had a reason to influence him. Thank you very much. Few individuals have so seamlessly embodied the confluence of ancient Indian wisdom and modern scientific inquiry as does Professor Manjul Bhargava. His work, beginning with the groundbreaking generalization of Gauss's composition laws, has not only expanded the frontiers of number theory, but also rekindled the timeless Indian fascination with mathematical beauty and abstraction. His recognition with the Fields Medal only confirmed as one of the most brilliant mathematicians of our era. Yet what makes Professor Bhargava truly special, and in the meeting that I had with him, that special part came through so sharply, is that he situates his intellectual journey within India's civilizational continuum. Drawing inspiration from Sanskrit texts, he was taught Sanskrit by his grandfather in Jaipur. Classical music, he's an accomplished tabla player, learned from Ustad Zakir Hussain. And the creative imagination of the Indian mind that has for millennia sought patterns between the metaphysical and the measurable. Today's theme, India's Scientific Imprint to the Globe, invites us to reflect on that continuum, from the geometry of the Sulba Sutras to the algorithms of Panini, from Aryabhatta's vision of the cosmos to the contemporary innovators shaping our technological future. It reminds us that India's contribution to global knowledge has never been confined to one discipline or epoch. It has been a living dialogue between science, philosophy, and society. Professor Bhargava, we are deeply grateful that you have found time amidst all your commitments. Your presence will inspire the School of International Studies in its 70th year, but also our students and all of us who believe that life of the mind must be wedded to the larger quest for the good and the beautiful. Ladies and gentlemen, please join me in warmly welcoming Professor Manjul Bhargava.
Maybe we can dim the lights. Let's see it. Well, thank you very much, Professor Mattoo, for the very kind introduction and introductory words. It's a great honor to be at this very important conference on India and the world order, preparing for 2047. On this occasion of the School of International Studies' 70th year, many congratulations to SIS. I know it's not very often that a scientist or mathematician gets invited to one of these conferences, maybe for good reason, I don't know, we'll find out. But I want to thank all the participants and of course Professor Mattoo and the organizers for thinking of me, for having me, for the invitation to speak here, and for having a scientist and mathematician represent. It is indeed interdisciplinary thinking, as Professor Mattooji said, that will be critical for India's vision for 2047. And of course, science and mathematics will be a very important part of that interdisciplinarity. As already mentioned, India has a huge scientific imprint on the globe, going back thousands of years, from ancient times all the way to modern times. So, for example, India's scientific imprint on the globe extends from seminal ancient contributions in mathematics, metallurgy, chemistry, astronomy, medicine, yoga, meditation. These are all ancient contributions that have had a profound impact on the globe, but also coming to modern achievements in fields like physics, computer science, space technology, vaccines and pharmaceuticals, agriculture, digital infrastructure, and so on. So India's had a vast scientific imprint on the globe, one that we don't always learn so much about, we don't get to hear so much about, but it has been very, very impactful on the way science happens around the world. And this continuing influence of Indian science is amplified by its large scientific diaspora around the world, in the areas of technology and in science. And it's also amplified by its increasing international collaborations. More and more Indian scientists collaborate with scientists and engineers around the world. And so the scientific imprint is ongoing, and it's something we really should know about and use it to plan India's vision for where it should be in 2047. So one question that I'm often asked is, why is it important to know about India's contributions? Can't we just use the science as it comes to us? Science is often viewed as just a utilitarian field, but we don't really need to know its history, its Indian origins. So why is it important to know about India's contributions? So in my mind, the purpose of studying India's contributions to science and beyond, the connections of science with other fields, why it's important to study those contributions is, first of all, a lot of us are academics here, it's to know what is correct and accurate in the history of knowledge. So just from a historical standpoint, to know what is correct is important. But another aspect of understanding India's impact, scientific impact on the globe, is to develop a pride in India that can then be used to further inspire its people, especially its young people. Understanding the history of science also improves learning, not just in science, but across subjects. If one learns the roots and foundations of the subject, that helps us in learning the subject better. So if one knows where ideas came from, how they originated, then we actually learn those concepts better, and we actually gain the ability to innovate further, to use that kind of thinking in developing new research. And just from an educational standpoint, learning is far more effective, far more relevant and useful when it's rooted in the local context. When in school we learn that certain concepts developed through local arts, certain scientific concepts developed through local arts, through local crafts, through local thinking, through local philosophy. When it's rooted in that local context, then students actually learn better. So these are some of the reasons why it's important to know about India's contributions, but one last important reason is that studying India's contributions to science and beyond, the purpose is to develop an important type of scientific soft power that can be used for the good of the country and the world. So knowing the scientific contributions that originated on this soil actually gives India a certain soft power that it can use for good, both within the country and beyond. And there are many examples of this that have already materialized, but there are many others that have not. So some examples from ancient India, perhaps the one that's most well known around the world, the scientific method of improving one's body and mind, for developing one's body and mind, the scientific system of yoga, has been rightly reclaimed in recent years. There's now an International Day of Yoga, which has improved the lives of crores of people around the world through better mental and physical fitness. But it's also, while it's helped the world in a great way, it's also helped India in a big way. For example, economically. More yoga-related products originate now in India. Tourism has increased. Medical tourism, yoga-based tourism has increased in India. So this is something that's helped by claiming and reclaiming yoga as originating in India and understanding its roots and teaching yoga through its roots has improved the lives of millions around the world as well as in India. But there are many other contributions of India that have not been so rightly reclaimed, and there is great potential lying in that reclaiming. Metallurgy is one area that India contributed great strides to over thousands of years. The Iron Pillar of Delhi is one great testament to the great understanding of working with metal that existed in India centuries ago. And that technology is still useful today. And then, of course, perhaps one of the greatest inventions ever, zero and the Indian number system, is something that has not been actually clearly attributed within India to having been developed in India. Zero and the Indian number system is something that's used around the world, and yet in India, sometimes we still we consider them as being of European origin or of Arabic origin when they're referred to the Arabic numerals. So I'll talk a little bit more about that. Being a mathematician, this is one that's close to my heart. So yeah, zero in the Indian number system, one of the greatest inventions in the history of the world. And I just want to say, when we talk about these Indian contributions, accuracy is of paramount importance. any claims that are made about Indian science, when they're used for education, when they're used to reclaim a soft power, accuracy is of the paramount importance. Primary sources have to be cited whenever such claims are made, and they have to be interpreted, translated accurately for them to have the power that they deserve. So having said that, let's go. I want to go back to, okay, so what are some of the great discoveries of India, and what is perhaps the greatest human discovery of all time? I may be biased since I'm a mathematician, but what is the greatest human discovery of all time? Well, the wheel is certainly up there, as often people say. But another one that is equally important, if not more important, in modern development, and is round as well, is zero. Yeah, is absolutely. So the zero, I think, is one of the absolute greatest inventions of all time. And the way that zero is used as it was developed in India is one of the greatest inventions of all time, if not the greatest human discovery of all time. And why is that? And it's something that India should be very, very proud of. And in a sense it is. It is a contribution, at least in words, that everyone does know. So the concept of zero originating in India is, of course, well known. A lot of us may have seen the T-shirt that many Indians proudly wear saying, India's contribution to mathematics is zero. And some of these T-shirts even have a subtitle that says, "We always knew we were good for nothing." And I'll show you a picture of this T-shirt in a moment. And while the statement about zero coming from India is true when interpreted correctly, and the concept of zero was there in some forms in other civilizations, in the Mayan civilization, for example, but what India did with it and how it originated in Indian thinking, starting with philosophy, going to architecture, then going to linguistics, and then coming to mathematics, really changed the world in a way that's really hard to overestimate. So that's the first point I want to make, is that zero really, really changed the world, but it's actually still only one of a very large number of fundamental contributions to mathematics coming from India. And so I want to outline some of those contributions today. And while the contribution of zero to mathematics is recognized and taught in schools around the world these days, including in India to a smaller extent, most of the other major contributions of India in mathematics and science usually go completely unmentioned, even in schools in India. But as I said, it's very important to bring those contributions to the fore for the purposes of education, for the purposes of knowing what's true, and for the purposes of using soft power, India's soft power, in a way that helps all. So today I wanted to point out some of those other fundamental discoveries in mathematics that were made in India and that I feel we all should know, and indeed that I feel should be taught in school. So first I'll just show you quickly. This is that famous T-shirt, if you haven't seen it before. So zero is India's contribution to the world. We always knew we were good for nothing. It's there at the bottom. But here are 10 non-zero Indian contributions to mathematics that I feel everyone should know. So zero is number zero there, but there are 10 others. The Indian number system, the way we all write numbers today around the world, originated in India. The Pythagorean theorem that we all learn in school is actually stated and proved well before Pythagoras by Bodhayana. So that's the Bodhayana-Pythagoras theorem. The mathematics of language and linguistics, theoretical linguistics, has its origins in India. A lot of the origins of trigonometry, including the fundamental function of trigonometry, the sine function, originated in India. Negative numbers originated in India. The solutions to quadratic equations. The way we count complicated quantities using binomial coefficients, that originated in India. The Fibonacci sequence that we all hear of was actually discovered 500 years before Fibonacci by Virahanka in the context of art and poetry. So that's why it's written here as the Virahanka Fibonacci sequence, ubiquitous in science. Error detecting and correcting codes were first used in a sophisticated way thousands of years ago to preserve oral manuscripts. And here's something that's often also not known by the general public, is that the first exact formula for pi. So what is pi? Pi is the ratio, if you take any circle, if you take the length around the circle and divide it by the length across the circle, that's always just one number called pi. Many civilizations approximated pi, often to many decimal places, but the first exact formula for pi, a very beautiful one, was first discovered in India. And so I'll say a little bit about each one of these things, just maybe a minute each. But first, let me start with 0, because we all know that 0 originated in India, but what exactly does that mean? I just want to say a little bit about what that means. So 0 and the way we write numbers today comes from India. The way we write our numerals today, called the Indian number system or the Hindu number system, originates in India. Hindu here refers to the geographic region around the Sindhu. And so around the world, these numbers are called the Hindu numerals. And it is perhaps India's greatest contribution to daily life. The ingenuity of the Indian number system is that any number, however large, can be written using only 10 symbols, namely 1 through 9 and 0. Just think about that for a second. No matter how big or how small a number you want to write, you can write it using just a finite number of symbols, no matter how big the number is. That's remarkable, and it's a vast improvement over other numeral writing systems that were developed in other parts of the world. For example, the Roman numerals, where to write larger and larger numbers, one needed to introduce more and more symbols. Right? So when you got to 10, you introduced a new X, and then when you got to 50, you introduced a new, and then when you got to 100, you introduced a new symbol, C, and then you got to 500, you introduced a new symbol. And then eventually, if you want to write a number that's too large and you've run out of symbols, you can't write them anymore. And that's one reason why most other parts of the world never wrote numbers that were larger than the thousands, because the number of symbols available was running out. The fact that one can now write using the Indian numbers any large number just using a finite number of symbols is what really changed the world and what made all technological innovations possible. To be able to work with arbitrarily large numbers without running out of symbols to write those numbers. So this remarkable Indian system of numeration, which we use today to write any number with only finitely many symbols, is truly what made all modern science and technology possible. The first surviving reference in which the Indian system of numeration was used is the Bakshali manuscript, which goes back to around the year 300. And there you can see the 0 being used almost like as it is used today. The 0 was written as a dot rather than a circle, because it was more used as a placeholder rather than a number in its own right. But that changed over time. I'll just skip that point here. Aryabhatta used these numbers just as we do today. And when did 0 become not just a dot and a placeholder and started to become an actual number like any other number? That was the work of Brahmagupta. In the Brahmaspurta Siddhanta, in the year 628, Brahmagupta described 0 as being a number just like any other number. You can multiply it, you can add it, you can subtract it, just like any other number. And it was after that introduction of 0 as a regular number just like any other number that this dot representing 0 started to get bigger and bigger and became a circle that's equal in size to all other digits, in recognition of the fact that it's just as important, if not more important, a number than any other number. So that was in the year 628, where 0 first became recognized as a number in its own right. And this Hindu number system was then transmitted to the Arab world by around the year 800. So it took about 500 years for it to go outside India, but by around 800 it was used by everybody. It's referred to in novels and other works of art. So it became commonplace amongst the people in India, and then around the year 800 it was transmitted to the Arab world. It was popularized in the Arab world by the great Persian mathematician Al-Khwarizmi, who wrote this famous book on the calculation with Hindu numerals, and by the great philosopher Al-Kindi, who wrote a very important book on the use of Hindu numerals that popularized the use of Indian numerals to do calculations in the Arab world. And then from the Arab world, about 300 years later, in around the year 1100, it was transmitted to Europe. And even in Europe, it took about another 400 years before it became accepted over the Roman numerals. But by the time of the Renaissance, it became so important to be able to do complex calculations that it was impossible to keep the Roman numerals around. And the Indian numerals were adopted across Europe, and then the rest is history. It took over the world. The Europeans, of course, learned the numerals from the Arabs, and so they mistakenly called it the Arabic numeral system, whereas the Arabs themselves used to call the numerals Hindasa, as the works of Al-Khwarizmi and Al-Kindi show. And so the Europeans mistakenly called it the Arabic number system, and then during the colonial times, the whole world started calling them the Arabic number system, including in India, where we often still call them the Arabic numerals. But this is finally being corrected in textbooks, in the new round of textbooks that are being developed now, with the correct history given. But this is a very beautiful story. I've only told you a very small part of it. How did the zero concept come up in India? In the first place, it came from philosophy, through yoga, the idea of achieving shunyata, emptiness, when one is meditating to achieve a state of mind that's empty of all emotions and thoughts. It originated there, it's made its way through architecture, through linguistics, and then eventually made its way to mathematics. A beautiful story originating in art and philosophy that we're now finally learning in schools, and it's something that India really should reclaim because it's completely changed the world. It's made all modern science and technology possible. I already mentioned the Pythagorean theorem. Everyone's seen the Pythagorean theorem before. If you have a right triangle with sides a, b, and c, then c squared is a squared plus b squared. And this is named after Pythagoras from about 500 BC, but there's a work called Badhayana's Shulba Sutra in 800 BC, where the Badhayana Pythagoras theorem is stated just as we learn it today. So it says a rope stretched along the diagonal produces an area which the vertical and horizontal sides make together. And that's exactly the modern statement of the Badhayana Pythagoras theorem. And there's even a verse that describes why the theorem is true, in a sense, a proof of the theorem, going back to 800 BC. So that's the Badhayana Pythagoras theorem. I want to point out that there's been mathematical contributions beyond just science, but in areas such as language and linguistics. So there's a notion of generative grammar in computer science, which essentially is a system of rules that generates exactly those combinations of sounds or words that form grammatical sentences in a given language. That's what a generative grammar is. And where did the notion of and that's something very important in computer science and modern theoretical linguistics. But where did the idea of generative grammar come from? It came from the work of Panini around 500 BC, who constructed a monumental generative grammar with algebraic rules governing every aspect of the Sanskrit language. It's the only time a generative grammar has been made for a natural language. It was the first time it was done at that time, and it's never been done again since. But the ideas behind it are used throughout computer science. So Panini Jashtadhyay consists of about 4,000 sutras over 8 chapters laying down a generative grammar for an entire natural language, something that's never been done for any other language. It was an incredibly ingenious way of describing an entire language just in one book, which you can put into a computer and it just generates all grammatically correct sequences of sounds or phonemes in an algorithmic way. And so for this reason, Panini is often called the father of linguistics and the early founder of theoretical computer science. One of the most amazing works ever written, combining mathematics and language. So these are the 4 I just talked about: zero, the number system, the Badhayana Pythagoras theorem, the mathematics of language. I'll just go through quickly some of the other 10. The sine function trigonometry was first introduced by Aryabhatta in the year 499 in his Aryabhatiya. The negative numbers, when Brahmagupta decided that 0 should be a number, so before it used to be that just 1, 2, 3, 4, 5, and so on were considered numbers. Brahmagupta said, well, 0 is also a number, and you should be able to add, subtract, multiply it. But then why stop there? Why not go even more back from 0? And he introduced the negative numbers, which of course changed mathematics, because now you can subtract any two numbers and you still get a number. You can add any two numbers and you still get a number. It formed what in modern mathematics is called a ring, and that really is what revolutionized algebra. So that's Brahmagupta's work from the year 628, the introduction of negative numbers. Brahmagupta also gave the first solution to the general quadratic equation. We all learned this formula in school, right? If you have a quadratic equation, minus b plus or minus square root of b squared minus 4ac over 2a. We all learned that in school. We learned it for the exam, then we promptly forget it right after. But in verse, this formula was written by Brahmagupta. And when you learn that verse, then you never forget the formula because it's written in verse. And that's how they used to learn it back in the year 600, something we've now forgotten. Now we mug up these formulas that we promptly forget. But if you remember the verse once, you never forget the verse. And that's how Brahmagupta originally wrote the quadratic formula. And again, it's something we don't learn in school, that the quadratic formula actually originated in India. But it was written in verse for the first time by Brahmagupta in the year 628. Binomial coefficients are what are used to count in the field of mathematics called combinatorics. And amazingly, they were introduced by Pingala in a work of linguistics back in the year 500. There, Pingala described a way to generate these binomial coefficients, which is still used in algorithms today. And then an exact formula for these binomial coefficients was given by Mahavira in the year 850. Both of these great advances in the area of combinatorics happened in India. I already mentioned the Virahanka-Fibonacci sequence was first discovered in the context of poetry by Virahanka in the year 600. Now there's an entire journal about Virahanka numbers that comes out every quarter. They're so important throughout science. As I mentioned, error detecting and correcting codes are written about extensively in Pingala in the year 500 BC as a way of preserving oral traditions, oral manuscripts. So when we pass down oral verses from one generation to the next, how do you ensure that bits don't get flipped and the verses are passed down incorrectly from one generation to another? Well, Pingala introduced these certain redundancies so that if there's any mistake in passing down a verse orally from one generation to the next, you'll catch the error and you'll be able to fix it. And these were the first such codes, which are now so important throughout communications and in space exploration. But these were first used by Pingala back in the year 500. And the ideas that were brought up back then are still used today. For example, NASA missions often use these error-correcting codes in almost the same way that they were first developed in 500 BC. And then maybe the last one I want to tell you about is the first exact formula for pi, which was discovered by Madhava in the year 1400. So over thousands of years, mathematicians from many cultures increasingly gave more and more accurate estimates for this most important constant, the ratio of the circumference of a circle to its diameter. So this ratio of the length of a circle, the circumference of a circle divided by the diameter, is a constant called pi, which is approximately equal to 3.1415926553358979323846264333327951058209, and so on. And that's just an approximation. So no matter how many decimal points you say, that will only be an approximation. And people got better and better approximations to this important constant. But the first exact formula was given by Madhava in the year 1400. And this is something that we all should learn. I mean, there is an exact formula for pi. And it was first discovered by Madhava, and it changed modern mathematics because this was the first introduction of the area of calculus, which we're only just learning about now. We always learned that calculus was invented by Newton and Leibniz. And of course, they made great contributions, but they were preceded by Madhava, who first laid the foundations of calculus, whose translations have only been happening in the last decade or so by Ram Subramaniam and M.D. Srinivas and Professor Sriram and others. Just in the last decade, we've learned about these translations. And so this first exact formula for pi that laid the foundations of calculus is right here. So pi is equal to 4 times this beautiful expression. It's an infinite expression, but 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9 minus dot, dot, dot. So if you evaluate that series and multiply it by 4, that's exactly equal to pi. Isn't that a beautiful formula? And you can calculate pi to any number of decimal places by just taking the series far enough. So this is the first exact formula for pi ever given, and it allows you to calculate pi as accurately as you need for any purpose. So this is the first and perhaps the simplest and most beautiful exact formula for pi in history. And it was discovered by Madhava in around the year 1400 in the context of his theory of infinite series, which indeed laid the foundations of calculus that would be discovered by him and started by him, now known as the Kerala School of Mathematics. This is now an active area of mathematical research, of research in the history of mathematics, and it's become active only in the last 10, 15 years or so, as translations of the Madhava school have been taking place, of the works of the Madhava school have been taking place, revealing a huge amount of mathematics that was known in India that we just didn't know about before, because the language in which this mathematics was written is a mix of Malayalam and Sanskrit, and so the only people who could really understand it are those familiar with Malayalam and Sanskrit and mathematics. And it took a while for a good team of such people to get together and do these translations, and it's mind-blowing. So if you haven't seen this before, I urge you to read more about it. It's quite a remarkable story and a fairly recent discovery in the history of mathematics. So there it is. So that's a summary of some of the major contributions of India to mathematics that I feel everyone should know. There's much, much more. That's just a summary of some of those things that come up in school. There are many things that don't come up in school that have had profound influences on science and mathematics. I'll just end with one last example. On a wall of the Parshnath Jain temple in Khajuraho is inscribed, and it was inscribed in around the year 1000, the following mathematical art. We've all seen in Khajuraho the beautiful visual art and carvings that are all around the town, this artistic town, but there's also a mathematical art that's inscribed on the Parshnath Jain temple in Khajuraho from around 1,000 years ago. So on the left there is that inscription. It's a photograph of the inscription on this Parshnath Jain temple. And you can see already back in the year 1000, they were using the Indian numerals just as we use them today. That's there in the Devanagari form. On the right, I've written them in the international form of Indian numerals. And so as you can see, what was inscribed there 1,000 years ago are the numbers 1 through 16 written in a 4x4 grid. So a 4x4 grid contains the numbers 1 through 16. And lots of people see this and they're like, okay, well, it's okay, they wrote the numbers 1 through 16. But they wrote them in a very, very special way, a way that it's hard to believe exists. So, I don't know if you can see this mouse here. If you add the numbers in any row of this square, okay, so all the numbers from 1 through 16 are here. If you add the numbers in any row of the square, for example, 7 plus 12 is 19 plus 1 is 20 plus 14 is 34, you get 34. Let's try the second row. 2 plus 13 is 15, plus 8 is 23, plus 11, 34. Again, if you add these two rows, you'll get 34. But it doesn't stop there. If you add the columns, you'll also always get 34. 7 plus 2 is 9, plus 16 is 25, plus 9 is 34. If you do this last column, if you do any of these columns, 14 plus 11 is 25, plus 5 is 30, plus 4 is 34. If you do the diagonals, 7 plus 13 is 20, plus 10 is 30, plus 4 is 34. 14 plus 8 is 22, plus 3 is 25, plus 9 is 34. So all the rows, all the columns, and the diagonals add up to 34. But it doesn't stop there either. If you take any 2 by 2 square inside it, for example, let's take 12 plus 13 is 25, plus 8 is 33, plus 1 is 34. Right? If you take any 16 plus 9 is 25, plus 6 is 31, plus 3 is 34. Any 2 by 2 square will add up to 34. If you take the 4 corners of the square, 7 plus 9 is 16, plus 4 is 20, plus 14 is 34. If you take the inner square, if you take these two plus these two, if you take these two plus these two, there are literally dozens of patterns of 4 numbers that if you add up, you'll get 34 in every which way. Isn't that amazing? How on earth did they come up with this? Why did they think that something like this will exist? It's almost a spiritual experience, finding all the ways that you can get 34, which may explain why it's on the wall of a temple. But it is an incredible mathematical discovery called the Chautis Yantra, or the 34 machine, because it generates 34 like a machine over and over again, every which way. This particular piece of mathematical history is something that was very important in my mathematical life, because I realized that first I was able to prove, for example, that there's essentially one such object, one such 4x4 object, and they found it. How did they think of finding it? I have no idea, but at least we can now explain that there is only one such thing. It's very, very special. And the other thing, when I worked on this, I realized that there's one such thing in every dimension. So if you go into n dimensions, there's one such object. And this is the one that you can write on a wall, and it was discovered over 1,000 years ago in India. And it has important applications to combinatorial design theory. And its generalizations have important applications to combinatorial design theory. And so again, it shows how many times when you look at ancient thinkers and the work they did, it can lead to breakthroughs even in modern times. And this is one such example. There are many such examples. Fractions were first introduced in India the way we write them today, 1 upon 2, 3 upon 4. That was first introduced in India. We see it already in the Bakshali manuscript in the year 300. Mathematical games like chess and knights tours originated in India, which have, of course, changed the world in many ways. Combinatorial algorithms, and much, much more. So there's a lot to say in a short time, so I'll stop there, and I just want to say that all of us should be aware of these kinds of things, as they're interesting, they're educational, they're historical, and they're India's soft power. So thank you very much.
Yeah. Thank you very much, Professor Bhargava, for that absolutely breathtaking, brilliant lecture, which disinterred in part all the Indian contributions to mathematics, but more in a larger context to the scientific world as we know it today. Every time I hear you speak on this, I get more and more inspired. And that's why I think your lecture should be is as much a part of our understanding international relations as those who are more focused on mathematics. I know we are running out of time, but if there are some pressing questions, people who want to, I saw Professor Ashok Guha there, or Brishti, you can do the, because I know you're both fascinated by numbers, so Brishti, go ahead, but quickly. Yeah, there's a mic.
Thank you for that very interesting talk. And it's nice to meet you again. I've met you in Princeton when I was a student there. So I am on the economics faculty here. And I just wanted to check if Fibonacci sequence can actually be traced back to Pingala, because from what I've researched, he had the Meru Prastara. If you look at the diagonals of the Meru Prastara, that will give you the Fibonacci sequence. So I know Virahanka was also involved, but I think it can be traced back to Pingala.
No, thank you. Good to see you again. And absolutely, Virahanka himself refers to Pingala. Pingala wrote his work in sutras, so they're very, very compact. There are some sutras there that clearly indicate the algorithm that generates the Virahanka Fibonacci sequence. But it's Virahanka who first sort of explicitly wrote down the numbers, explicitly wrote down the reasoning behind why the numbers are generated this way to count certain kinds of rhythms. So the first explicit mention of the numbers is in Virahanka, but the ideas can definitely be traced to Pingala. You're absolutely right. Yeah.
One more question. Is there someone? Yeah. Yeah, there's a girl here. Yes, please.
Thank you, sir. Myself, Shilpa Soni. I am PhD scholar of Center for West Asian Study.
Speak a little louder.
Myself, Shilpa Soni. I am PhD scholar of Center for West Asian Study. My question of how do modern perspective of Indian ancient legacy on the shape of education research pursued today?
I didn't understand the question. I don't expect Professor Bhargava to understand it.
Sir, my question: how do modern perspective on the Indian ancient scientific legacy on shape of education research and
I think
pursuit
that's a larger question. Maybe after on tea we can discuss that. But is there someone else? Yeah, Monica. And quickly, I'll just take two and the fun in front of you.
Yeah, thank you. This is Mallika Dasida. I teach at SIS. Just one clarification. Baudhyana, Pythagoras. Now, is it related to Buddha? Is it related to Buddha? Or it is just another name, Baudhyana?
Oh, Bodhayana is a different person than Buddha. Yeah. So
Definitely. Because
Bodhayana
you said 800 BC, so it's pre-Buddha.
It's pre-Buddha, yeah. So Bodhayana wrote this geometry book called the Shulba Sutra.
Exactly.
It's called the Bodhayana Shulba Sutra. So he's a separate person, lived in 800 BC, around 800 BC. He wrote the first geometry text of humanity called the Bodhayana Shulba Sutra. It was followed by 3 other Shulba Sutras by other authors, but his is the first Shulba Sutra. And in there he describes methods for constructing geometric shapes for fire altars.
Yes, my school knowledge, sorry for interrupting. My school knowledge says that Pythagoras' theorem was for geometry. Now, we all know Pythagoras' theorem, but not Baudhayana theorem.
Right.
Similarly, we do not talk about boson article, but Higgs boson.
Right.
So would you say Baudhayana, Pythagoras, and Higgs boson in the same plane? Because boson is India's contribution, boson theory.
Right. No, you're very, very right. And I mean, this is a general colonial legacy where names were often suppressed, history was often suppressed during colonial times to reflect a colonial narrative. And it is time to relook at history and to correct it and to give proper names. Sometimes we say that the name doesn't matter so much, but inside the name is the correct history. And if we use names that reflect the incorrect history, we're teaching things incorrectly and we're not often recognizing how ideas originally came about. So I completely agree. We should re-examine history properly through an Indian lens and not just the colonial lens, and rename things appropriately. The reason in textbooks, for example, they're now calling it the Baudhayana Pythagoras theorem. Not just the Pythagoras theorem, because that's incorrect history, but not just the Baudhayana theorem, because then the connect between all that the previous generation that knew it as the Pythagorean theorem won't understand what's being talked about. So Baudhayana Pythagoras theorem can be a transitional name, and then over time we can use the correct name, Baudhayana theorem. And I think similar things go for boson and Virahanka numbers and lots of other concepts that had different origins than how the colonial mindset had named them.
One final question, yeah. We're going to close it after that, yeah.
Hello, sir. This is Khushbu. I'm a final year PhD student at Center for European Studies, JNU. Sir, my question is to that you mentioned that Panini Sutras function as generative grammar that shaped the Sanskrit language. My question is that is it possible to create an AI, Indian version, using these sutras with the help of the Sanskrit language?
Oh, absolutely. I think there's already work done on putting in the entire Ashtadhyayi on computer, so that the computer can generate all grammatically correct phrases in Sanskrit. So that's a project that a number of different groups have been working on. So that work is already in progress, and I think there can be a lot of benefit once that is done in modeling languages generally. But that is work that's going on, and it could potentially be very, very important. But Panini's work already has had tremendous influence on just the theory of generative grammars, on computer science, the way programming languages are structured, and the way languages are understood, spoken languages are understood. But yeah, definitely, as AI gets better and better, Panini's insights can definitely be used in enhancing the way Indian languages, because a lot of the structure of Indian languages are modeled on the way Sanskrit, for example, the phonemes of Sanskrit, the sounds, are described in a very scientific way in Panini. When we teach computers to speak Indian languages and construct grammatically correct phrases in Indian languages. The way Banani modeled them, I think, will be very, very helpful.
Yeah, I think, okay, this Archana and the lady in the red, both of you, and then I'm closing this session because we have run into the coffee break, so you're most welcome to go and have coffee and come back because we're going to have the next session. Sorry? Okay, then quickly, 30 seconds each.
I'll also
Okay.
stay around after. We can talk over coffee.
And Professor Bhargava will be
I don't wanna-
available outside as well. Are you going to say?
Yeah.
And
I'll be
you
here.
should also use the fact that his wife is an alumni of the school as a way of getting access to him.
Okay.
So,
we'll talk.
Archana, you want to say something? Quick question? Quick question. Yeah. Mike. I mean, people are leaving the hall, but we'll continue.
Okay, I could do this over tea, but thank you so much. This was a fascinating mixing of math and history. I just wanted a factual clarification. There is a story which we often hear and I use in my teaching of exponential growth. The story of the and the grains of rice which get doubled on every box of the chessboard.
Right.
Does this have Indian origins? Because some sources say it's from Iran and some claim it's from other parts of the world, but do you know if there is a direct connect to an Indian origin to this theory of exponential growth?
Yeah, there are many works. I don't know the first instance where this came up, so that is worth researching. But there are definitely many works that refer to the story of a king saying that he will grant 1 grain of rice on the, I mean, it's requested of him. A reward is requested of him that please just give me 1 grain of rice on the first square and then double it for each subsequent square. And that's all I ask from you. And the king says, oh, that's all you want? Sure, I'll give it to you. Not realizing that if you start with 1 grain of rice and double it 63 times, that it'll be more rice than has ever been produced in the history of the universe. So that's a story of exponential growth that occurs in many Indian works, but I don't know where the first occurrence of that story is. That's something that's worth finding.
Would you like to postpone it over tea, or you want to say it?
Okay, maybe last question. Then we can talk over tea.
Tea.
Yeah.
Professor Bhargava will be available for tea.
Welcome to JNU, Professor Bhargava.
Thank you.
I'm a linguist,
Good to be
so
back.
my question is directed towards this because you mentioned linguistics at least 4 times, and then obviously towards the end also you mentioned about it. How much of the knowledge of linguistics has helped you in the mathematical world? And you being the advisor as far as education is concerned to the government of India, why is it that linguistics is not being taught in the bachelor's and the graduate level as compared to other subjects? So if you could give us a kind reason and could also advise the government to introduce that, it would be great. Thank you so much.
Great suggestion. Thank you. Linguistics has definitely been a very, very strong area that India has contributed to more than any other region in the world, and including mathematical discoveries by Panini, by Pingala, by Virahanka, Gopala, Hemachandra, all linguists who contributed incredible things to mathematics through their linguistic thinking. And India doesn't, yeah, you're right. It's not been taught in schools in the past. It is being introduced now to some extent. But you're right, in higher education, we need far more linguistics departments. That entire area of Indian study has been ignored for a long time. I would certainly encourage the government personally to have more representation of linguistics. Yeah, thank you. Yeah, absolutely. So,
Thank
yeah,
you
that should
very
definitely be
much to you, Professor Bhargava, to the audience. And we'll do a quick switch over and start the next session in 5 to 7 minutes on India's economic ascent and implications for the world, which is going to be chaired by the Chief Economic Advisor to the government. And I see Professor Sanjeev Sanyal and Professor Prabir Dey and Professor Amitabh Bratra already here. So we'll reconvene in 10 minutes, and thank you so much.